In this video, I'm going to talk about family pedigrees. Family pedigrees show the inheritance pattern of a particular trait in a family. So for example, in this family here, we can see that individuals that are shaded in have a certain trait that we're interested in. And we can see how that trait has been inherited from one generation to the next. Now, why is this important? Well, scientists have to actually look at the inheritance pattern of certain traits to figure out if they're caused by a dominant allele or a recessive allele. So remember that every single trait that an individual has, every physical characteristic, disorder, or so forth, is caused by two copies of a gene. So we have two copies of a gene that controls every trait. Now, these two copies of the gene could be identical or they could be different from each other. So they could have slight variations, which we call alleles. There's two different variations that are typically possible. One we call a dominant allele, and it will always be expressed if it's present in an individual. And the other variation of the gene is called a recessive allele. A recessive allele will only be expressed or shown in an individual if the individual has two copies of it. So remember, the goal of these family pedigrees is to determine if a trait is caused by a dominant or recessive allele. This is what we don't know, so this is why we do this, okay? So a lot of times students make the mistake and they think that if an individual's colored in, that means they have the dominant, they're expressing the dominant allele or the dominant trait. However, that does not mean that. We don't know if this trait is caused by a dominant allele or recessive allele, and that is why we have to look at these inheritance patterns. So when we're looking at a family pedigree, there's a couple symbols here that you should be familiar with. Any square that you see is a male. Females are represented by circles. Anytime we have a mating pair, there's a line between them. And you can see that we have a mating pair here. There's a mating pair here. And there's a mating pair here. So there's three different mating pairs in this pedigree. So we also could see where we have children. So anytime there's a line coming down from a mated pair, then that means that those are their children. So this pair here has 3 children, 2 sons and a daughter. This mating pair here has 3 children, 2 sons and a daughter. And you can see that this daughter married this male here, or mated with this male. And then these 2 individuals had 2 children. Once again, anything that's shaded in represents individuals that has the trait or the disease that we're interested in. And any individual that's not shaded in means that they are unaffected. They do not have the trait or they do not have the disease that we're interested in. So let me give you some tips for solving these family pedigrees. First off, what you want to do is you always want to look for somewhere on this pedigree, there must be 2 alike parents. So that means these 2 parents look similar to each other. They both have the trait or they both don't have the trait. They're both shaded in or they're both not shaded in. And they have at least 1 child that's different from them. So as long as there's at least 1 child different from them and both parents look the same, then we know right away that the only way you could get that inheritance pattern is for both of the parents to be heterozygous. So let's look down here. Do we see that anywhere? Well, in the first family here, they all look alike, so we can't use that family to use this kind of trick. But if we look here at the first family right here, we can see that these parents look identical. They both don't have the trait. They're not shaded in. They're both unaffected. And they have at least 1 child that has the trait we're interested in. So what does that tell you right away? These parents have to be heterozygous. That is the only way that we could see this type of pattern happening. Now, an important thing to note is that if you don't have this type of pattern somewhere in the pedigree, then that means there's not enough information in that pedigree to know for sure if the trait's caused by a dominant or recessive allele. You need to have this pattern to know with 100% confidence whether the trait's caused by a dominant or recessive allele. In order to figure out whether it's due to a recessive or dominant allele, there's a couple different tricks that we'll go over. But one thing that you can look at is if a child has a trait but both parents don't, then you know the trait has to be due to a recessive allele. So in the example that we have here, we can see that the child has the trait, but both parents don't. So what that means is that this trait was hidden in the parents' generation. And the only way that a trait can be hidden in both of the parents and then a child get it is for that trait to be caused by a recessive allele. And so that means that this child here got both recessive alleles. It got one from each parent. So the child is expressing the recessive allele, whereas both parents are expressing the dominant allele. So anytime you see that pattern, we know that the trait we're interested in is due to a recessive allele. And then you also know that every individual that's shaded in this pedigree also is expressing the recessive allele, so they all must be homozygous recessive. Every individual that's not shaded in is expressing the dominant allele, so they have to have at least one big letter. We might not always know what the second letter is, and sometimes we will, but we just know that right away by looking at the patterns we see here. On the other hand, if a child doesn't have the trait, but both parents do, in other words, the child's not colored in, but both parents are shaded, then the trait is due to a dominant allele. So we just talked about this pedigree, but I just thought about something else I wanted to mention to you. So when we just did this pedigree, we realized that these parents have to be heterozygous because they look alike and they have an offspring that's different than them. The offspring has to be homozygous recessive because it has both of the recessive alleles, and it's expressing the recessive allele, whereas the parents are expressing the dominant allele because they're heterozygous. We know that every individual, we said, that's shaded in has two little a's, and every individual that's not shaded in has to have at least a big A. Well, what if we wanted to know what this female was? Do we have enough information to know what she is from looking at this pedigree? So anytime you get to a situation where you're looking at somebody expressing the dominant allele, your goal is to figure out, are they big A, or big A, little a, or is there not enough information to tell? Sometimes there isn't. Like, for example, like this individual, this female here, she could have gotten a big A and a big A from each parent, or she could be big A, little a. She would still be expressing the dominant allele. But what about this female down here? Do we know what her genotype has to be? Well, if we look up at her parents, we know she had gotten one allele from each parent. Well, she had gotten the dominant allele from her mom, but what is the only allele she could have gotten from her father? The only allele she could have gotten was a recessive allele, so this female has to be heterozygous. So if you're ever asked a question like that, always look at the parents or look at the offspring to try to figure out what an individual is. Oh, wait a second. We actually know what this female could be too, because look at her offspring. She produced an offspring that had two little a's. So this female must be also heterozygous. So once again, always look at the parents and always look at the offspring, and sometimes that can give you information and let you know what the genotype of an individual is. This is example 16 on your handout. It says the figure below shows the inheritance pattern for two different traits. And these traits could be anything. Let's just pick some traits here. Let's say this is dimples. And here we're looking at freckles. So I just picked some random traits, and it could be anything. So what do we know here? Well, we know in this left one that this son here has dimples. And we know that because he's shaded in. So every individual that's not shaded in doesn't have dimples. Over on the right side, we know that these parents have freckles because they're shaded in. Their son has freckles, but then their other son and daughter do not have freckles because they're not shaded in. So here we're lucky because we have enough information in both of these pedigrees to know whether the trait is due to a dominant or recessive allele. And that is because we have the pattern that we need to have here. In both cases, the parents look alike and they have at least one child that's different than them. So what do we know if that's the case? Well, in this case, we know the parents have to be heterozygous. That's the only way that this is possible. So let's make a little key here. So on this side, big D would equal, well, we know if the parents are heterozygous, that any individual that's heterozygous is always showing whatever is controlled by the dominant allele, right? So what do these people look like? Well, these individuals don't have dimples because they're not shaded in. So big D would have to equal no dimples. Well, what does that mean little d equals? Well, that means it has to equal dimples. So, since we know little d equals dimples, what does this individual here that's shaded in, what does their genotype have to be? Well, they have dimples, they're shaded in, and we know that's caused by recessive allele. The only time an individual could be showing or expressing the recessive allele is to have 2 copies of that gene. So we know that this son is homozygous recessive. We know that dimples is caused by a recessive allele. Let's look at another example over here. So here we again, we're looking at a different trait. We can see that both parents have the trait. So they have freckles, but they at least have one child that doesn't have freckles. So because this is a pattern that we're looking for here, we know the parents have to be heterozygous. That's the only way that they could make a child that doesn't look like both of them. So what do we know? Let's make a little key. Big F would have to equal, well, since both the parents are expressing the big F, what do they look like? Well, they have freckles. So big F equals freckles. Right away, we know then that freckles has to be caused by the dominant allele. Little f would equal no freckles. So not having freckles is caused by the recessive allele. So what do we know about these 2 children that are not shaded in? Well, they have to be homozygous recessive. So they're expressing the recessive allele, which is why they look different than their parents who are expressing the dominant allele. What about this child over here? Well, this child over on the left has to have a big F because it looks like their parent. So they have freckles. And we don't really know what the second letter is because they could have gotten a big F from their dad and a big F from their mom, or they could have gotten a big F from their dad and maybe a little F from their mom, and they still would have freckles. So sometimes you don't have enough information to know exactly what an individual is. So in here we're looking at example 17. And in this example, we're looking at a trait called I think there's supposed to be a P here. Hypercholesterolemia. So it's asking us, is it due to a dominant or recessive allele? Well, where do we begin? We're going to look for somewhere in this pedigree where there's 2 parents that look alike and they have at least one offspring that's different than them. And I actually see that right over here. These 2 parents look alike and they have at least one offspring that's different than them. All right, so what do we know right away? We know that these parents have to be heterozygous to make that happen. So I'm going to just write that in. That's the first thing I do. So we know that the parents are expressing the big H because they're heterozygous. What do the parents look like? Well, since they're shaded in, that means they have hypercholesterolemia. So I'm just going to abbreviate this as hyper. So this means having little h means you're not hyper. You don't have hypercholesterolemia. So is hypercholesterolemia due to a dominant recessive allele? Well, we can see right here that individuals that have hyper have to have the big H. So it is due to a dominant allele. If the female starred married a heterozygous male, what is the probability of their child having hypercholesterolemia? Well, if we look over here, we have to first figure out what this female's genotype is. Well, we know that she doesn't have hypercholesterolemia. So let's look up at our key here. Well, not having it is caused by the little h. So the only way that she could not have it is to have two little h's. So it's asking us if she mated, let's do a little Punnett square up here. If she mated with an individual that was heterozygous, what's the chances of their child having hypercholesterolemia? Now we're just going to do a simple Punnett square. So what gamete could she give her offspring? Well, she could only give her offspring a little h. What could this parent give? Well, he could give a big H, or he could give his offspring a little h. So let's set up a little Punnett square. So I'm going to put her possible allele up here on the top, his down here on the side. The possible offspring would be big H, little h, or little h, little h. What is the probability the first child will have hypercholesterolemia? Well, if we look over here, hypercholesterolemia is due to the dominant allele. So it looks like this offspring would have it, and that would be 1 out of 2, so a half. The probability is a half, or 50%. And that's your answer. Let's look at another example looking at pedigrees. Is cystic fibrosis due to a dominant or recessive allele? Well, if we look in the family pedigree, we got to look for that specific pattern again, with two parents alike, and they have at least one offspring that's different than them. And I actually see that right over here. These two parents are alike, and they at least have one offspring that's different than them. So what do I know about the parent's genotype? What genotypes do they have to make this type of pattern possible? Well, they have to be heterozygous, both of them. So I can just write that in right away. We always know from just knowing the rules about genetics, if an individual has a big F and a little f, they're going to ignore the little f, and they're always going to just express or show the big F. So what do we know about this then? Big F equals, well, what do the parents look like? They're not shaded in, so they do not have the trait. They don't have cystic fibrosis. So that means little f causes cystic fibrosis. So is cystic fibrosis due to a dominant or recessive allele? Well, it's due to a recessive allele. Therefore, we know, since that's due to a recessive allele, any individual that has cystic fibrosis must have two of the recessive alleles for them to have the disease. Because every individual needs to have 2 copies of a gene, and to express the recessive gene, you have to have 2 copies of it. If the couple marked by the arrow had another child, what is the probability their child will have cystic fibrosis? So we know that both of these parents are heterozygous. We just set up our Punnett square like we always do before. What are the possible gametes this individual could produce? Well, they could give their offspring a big F or a little f. This individual could give their offspring a big F or a little f. So let's set up our Punnett square. I'm going to put the gametes from this parent across the top, the gametes from this parent down the side. If you're having trouble doing these monohybrid crosses, remember that I have a video up just going over how to do these, and you might want to go back there to learn how to do that. Or you can actually even go back all the way to the first video I posted, which just talks about genetics in general and some of the terminology we use, like dominance and recessiveness. So if the couple marked by the arrow had another child, what's the chance they have cystic fibrosis? Well, we know cystic fibrosis is caused by the recessive allele, so only a child that has 2 recessive alleles would have it. There we go. So the answer would be 1/4, or in other words, 25%. And there we go. Now we know cystic fibrosis is caused by recessive allele, and we know the probability that their next child would also have cystic fibrosis.